Hello everybody, so in this video I am going to show and discuss the conformation of cyclohexanes, okay? So cyclohexanes are 6-member rings hydrocarbons, as you can see in this picture, and the most stable conformation of a cyclohexane is a chair conformation. So let me discuss a few things about this chair conformation. So we call this a chair conformation since you could potentially imagine as this could be where you would be sitting, here where the legs are, and here is where the head will be. Okay, so this is the head of the chair, this is where it sits, and this is the legs of the chair. So why are cyclohexanes chairs so stable? So if you look at the chair conformation, the first thing that you will notice is that the bond angle in every carbon here is very close to 109.5, which is the optimal bond angle for sp3 hybridized carbons. So the angle strain here is very minimum, since once again the bond angle in every chair conformation for cyclohexane is very close to the optimal bond angle. The second thing that is very interesting about cyclohexane is that, as you can see in these structures, um, for example, let's look at this angle here and this one here. So the dihedral angle in between this bond here and this bond here is 60 degrees, right? The dihedral angle between this bond here and this next one here is 60 degrees. And that happens for every atoms or groups that are bonded to each carbon here. Therefore, in a chair conformation, every group is staggered, meaning that every groups or atoms bonding to the first carbon are as far as possible to those atoms or groups bonded to the back carbon. So a cyclohexane is in a staggered conformation, therefore it has no torsional strain. So what is the only potential factor that can destabilize a chair? So is what we call 1,3 diaxial interactions. So if you look at this cyclohexane chair, a few things about this are important. Number one thing is, in the head of the chair, there is a bond pointing straight up, and there is a bond which is to the side, right? So we call these bonds that are straight up or straight down axial bonds. So we have axial bonds, and we have also equatorial bonds. Those are the ones that are to the side of the carbon, okay? So in the head of the chair, axial is pointing up. Then in the next carbon here, the axial bond is pointing down. So you see how they alternate. In the next carbon, axial is up. In the next carbon, axial is down. In the next carbon, axial is up. And in the next carbon, axial is down. Meaning that in a chair conformation, the axial bonds, they alternate. In one carbon is up. In the next carbon, the axial bonds are in the opposite plane, pointing down. And the same happens to the equatorial bonds. So in the head of the chair, the equatorial, you can see how it's pointing down. So the angle is across, the plane is across this. Okay, so you can see how this is pointing down. Therefore, in the next carbon, equatorial must be pointing up. So above the plane, that's what I mean. Remember, the angle here is close to 109.5. So if this is straight down, this have to be slightly above the plane. In the next carbon, below the plane. In the next carbon, above the plane. In the next carbon, below the plane. In the next carbon, above the plane. So both axial and equatorials, they alternate. In one carbon, they are above the plane. In the next carbon, they will be below the plane. That's the number one thing to mention here. So in this specific chair, we have 3 actual bonds pointing up. I color coded them as you can see. So it's in carbon 1, 2, and in carbon 3 there is another actual pointing up. Carbon 1, 2, 3, there is another action pointing up, right? So this is what we call 1-3-3 diaxial interaction. What I mean by that is that if these atoms here in these 3 positions are just hydrogens, hydrogen is very small, there will be no destabilization whatsoever. However, if you have anything here in one of these positions that is different to hydrogen, for example, let's say an ethyl group. Now this ethyl group here, you cannot see it in this picture well, but you can see how this is now colliding, is smashing with these 2 hydrogens, and this is an aesthetic strain that will be destabilizing a chair. So in every chair conformation, 1-3 diaxial interactions are the only destabilizing interactions. And what exactly do we mean by that? Any substitution in actual position will have 1-3 diaxial interactions. The same obviously applies to the bottom. So there is a 1 axial here, 2 in the 3rd carbon, there is another axial bond, 1 carbon, 2, 3, another axial bond. So these 3, 1-3-3 axial applies obviously to the bottom plane and also to the top plane. So the second thing that I want to mention here is that every chair is in equilibrium with the flip chair. So every chair is always in equilibrium with a flip chair. So in the flip chair, what happens is that what was the head here now is brought down, so it becomes the legs. And whatever was the legs in one chair, in the flip chair, it will become the head. So I want you guys to really look into this and notice what happens to the axial and equatorial bonds. So I'm going to number the carbons. So this is carbon 1, let's say. This is 2. This is 3. It's 4. It's 5. And this will be carbon 6 for us. Okay? So these will be our carbons. And it's important to number them. You will see why later, because that's how you can keep track of what's happening in a chair and in a flip chair. So always make sure to number the carbons. Once again, 1, 2, 3, 4, 5, 6. Now let's assign numbers to the flip chair too. So carbon 1 in the flip chair is here. Carbon 2 in the flip chair is here. Carbon 3 in the flip chair is here. Carbon 4 is here. Carbon 5 is back here. Carbon 6 will be here. So it's very important, guys. Once again, keeping track of the carbon numbers is very important to minimize mistakes. So I want you guys to look into what happened to carbon 1. So when we bring this down here, the blue, which is the equatorial bond in the chair, is going now to axial in the flip chair. The brown, axial bond in the chair, it falls now equatorial in the flip chair. And that happens to pretty much every bond here. So anything that is axial is equatorial in the flip chair. Anything that is equatorial is axial in the flip chair. And one really important thing is up, and this is a saying for organic chemists. So up is up. and down is down in both the chair and the flip chair. And I will explain what I meant by that. So in carbon 1, once again, axial is above the plane, is pointing up. Equatorial is to the side below the plane. The plane is across here, okay? If we look at carbon 1 here, blue was in carbon 1 equatorial, is axial. Brown was axial, is equatorial. However, blue is still below the plane is across here. Brown is still above the plane. Brown above the plane, blue below the plane. So you go from axial to equatorial, from equatorial to axial, but up is up and down is always down. That applies for every single carbon in the chair and in the flip chair. Okay? So once again, in the flip chair, the three groups in axial position, so these two and these, the green groups now are, the three of them are axial. Anything different than hydrogen here will bring 1,3 diagonal interactions. The three blue are also axials. So anything here that is different than hydrogen will bring 1,3 diagonal interaction, making the chair less stable. So let me give you an example, because one of the key things here that every student must know is how to convert chairs into flat structures and vice versa. Okay, so I'm going to say now, let's say I'm going to put all hydrogens here at first. And then I'm going to replace two of these hydrogens. Let's say, for example, this one, I'm going to say here CH3. Okay, and I'm going to say here CH3. Okay. So, okay, so I'm trying to do this CH3, I'm gonna make it slightly longer so it doesn't clash here. Okay, so if I have this CH3 and this CH3 here, to translate, guys, this cyclohexane into a flat structure, we are going to look at the cyclohexane chair from the top. So if we look from the top, in carbon 1, this methyl is coming toward us, so we are going to use a wedge bond is coming toward us, and in this carbon here, carbon 2, the methyl group is going away from us, so this would be carbon 2. Again, if we are looking from the top, this is going to be to our left, so that's where the methyl group will be. Okay, so this flat structure corresponds to this cyclohexane chair. Okay, remember, when you have two groups in opposite planes, we call this trans isomer, because once again, the two methyl groups are trans. The name of this compound will be trans 1,2-dimethyl cyclohexane. If we flip this chair now, the methyl group that is in carbon 1 axial will be in equatorial, so it will be here. So let's place the methyl group here. And in carbon 2, the methyl group will be in this position. Sorry for that. So methyl group will be here. Okay. So in this case, it will be in diaxial in chair 1 and in diequatorial in chair flip chair. If you do, once again, guys, the flat structure will be exactly the same. Don't be confused by that. So if we look from the top here, in carbon 1, CH3 is coming toward us. In carbon 2, CH3 is away from us. So the flat structures give you the cis-trans relationship and the position of the carbons, in this case 1, 2. It doesn't tell you about conformations. Okay, so if we were to analyze from this 1, 2 trans, I'm gonna write over here trans 1, 2 dimethyl cyclohexane, which is the most stable conformation for this. So the most stable conformer will be this one, because in this conformation, the two bulky groups are in di-equatorial position. Everything else, remember, here is hydrogen, so I'm going to correct this here. Whereas in the chair, original chair, the two methyl groups, I'm going to show this now, the two methyl groups here are in axial position. So these methyl groups have a 1,3 diaxial interaction with these two hydrogens. This methyl group has 1,3 diaxial interactions with these two hydrogens. Whereas these two methyl groups are in the equatorial position, no 1,3 diaxial interactions, and therefore this conformation is more stable. So another example of this could be if I provide, for example, the flat structure of this cyclohexane. So in this flat structure, we have the 1,4 dimethyl cyclohexane. This is a trans, so I'm gonna draw it over here, trans. So if we want to determine the most stable conformation of this compound, first thing we're gonna draw is the chair conformation. So we can draw a chair. I'll draw the chair with you guys here, so I show you how to do this. So you draw two parallel lines, and then you can just put together the parallel lines at an angle. So that will make for the chair conformation. This is not a perfect chair, but you can tell. Okay, can make it better. And then the way to do, once again, axial and equatorials is in carbon number 1, which is the head carbon. Methyl group is pointing up. Sorry, in this case, axial is pointing up. Therefore, in the next carbon must be pointing down, up here, down, up, and down. I'm gonna label, color code this axial bonds in red, and then equatorial is in the opposite plane, so the equatorial must be down here, up, down, up, down, and up. Okay, so this will be chair. So now we're gonna put the groups here. So in carbon 1, we have a methyl pointing toward us. So that would be here, toward us is axial. And in carbon 4, 1, 2, 3, 4, 1, 2, 3, 4. The methyl group is away from us, so it must be over here. So in this chair that I drew, both methyl groups are diaxial. Obviously, they will be having 1,3 diaxial interactions with the remaining hydrogens. So I'm going to color code once again the diagonal interaction so everybody can see it over here. This will be having diagonal interactions with these hydrogens here. And this method will be having diagonal interactions with these hydrogens here. Okay? And this chair is in equilibrium with the flip chair, which I'm going to copy from here. You guys should know how to do now. So in carbon 1, the method was initially axial. In carbon 1, it must be equatorial. And then in carbon 4, so this is carbon 1, 2, it's going to just place the number here. Carbon 1 is here. And then carbon 4 is here. In carbon 4, the methyl is away from us, or it must be here. I will recheck my work. So in carbon 1, the methyl was initially axial, must be now equatorial. Correct. In carbon 4, the methyl is axial, must be now equatorial. So if I need to determine which of these two is the most stable conformation, so obviously this is the most stable conformation, so I'm drawing different equilibrium arrows here. So the one showing the longest arrow toward the most stable conformation. Why? Because here we have 1,3 diagonal interactions, whereas here both methods are equatorial. So this would be the most stable conformation of trans 1,4 dimethyl cyclohexane. So this is how you build and analyze conformation of cyclohexane. So you gotta always draw the chair, draw the flip chair, anything that is actually equatorial and vice versa. Up is up and down is down. And once you build both the chair and the flip chair, if you have substitutions, analyze how many diagonal interactions you have, and that will determine which is the most stable conformation. Thank you.